Hi, everybody. I just want to review the digestion physiology material very quickly. It's pretty much all laid out for you so that when you actually apply this material to the digestive physiology laboratory, it's a tongue twister there, hopefully it will make a little bit more sense and you'll be able to actually apply the knowledge. But, I know these diagrams look a little bit scary, but, this is the material arranged in as straightforward of a way as we possibly can. So it really isn't so bad. I would recommend just diagramming it out, like literally copying it over again, and then seeing how much you can reproduce on your own and how much of a story you can tell yourself as you go along and regurgitate this material. That's usually how you study for everything in biology, but I think that type of repetitive studying strategy is going to be especially helpful here. But I think that you'll find that once you get the general logic of it, that it really isn't so bad. So remember, digestion is just the process by which we're breaking things down. We can break them down physically. That's physical digestion, where we take big things and we break them down into smaller things, but those things actually don't change on a chemical basis, all right? So they still stay the same thing. So we talked about how bile emulsifies fat. In other words, it physically breaks it down. It takes big fat globules and it turns them into small fat globules. Now, chemical digestion is where you actually change the chemical nature of a material as you break it down. So you take a large molecule and you break it down into its subunit molecules. And you guys remember the subunit molecules for all of the major biomolecules from AP1, or at least you should be able to go back and reinitiate those memories of that learning that you had performed in AP1. So let's start off with carbohydrates. Carbohydrates is the big class of biomolecules that we're going to be talking about first. So the example that we're going to use first is starch. Actually, let me get the pen initiated here. I might stay with purple. It's fine. So we're going to start off with the biomolecule starch as our representative carbohydrate. We also have lactose and sucrose, which are disaccharides, whereas starch is a polysaccharide. But let's stick with starch first. So starch begins to be broken down by salivary amylase, which is an enzyme that's actually secreted as part of your saliva, as the name suggests. So digestion of the starch begins in the oral cavity, in this regard. Then we get to the small intestine, where the pancreatic juices also contain an amylase enzyme that further breaks down the starch. Now, starch is a polysaccharide of lots of glucose subunits linked one at a time, over and over and over and over and over and over and over again in branching chains, right? So this enzyme can't break down every single bond that links every single glucose molecule at once. And so it just starts breaking random linkages between glucose molecules in these very long, elaborate branching chains of the starch molecule. And so what you get is basically miniature starch molecules, otherwise known as dextrins. They're oligosaccharides, meaning they're not quite as big as the original starch polysaccharide, but it's still basically the same thing, just lots of branching chains of glucose molecules linked over and over and over and over and over again. So then what happens is we have intestinal enzymes that further break down the linkages between the glucose molecules until you finally get the disaccharide maltose. And if you guys remember maltose from AP1, we had a model of maltose. All maltose is just two glucose molecules linked together. It's a disaccharide. And by the way, these intestinal enzymes like dextrinase and glucoamylase, which you don't have to memorize. You don't have to memorize those terms, but they're just examples, so you know that they exist. Serves as an anchor so you guys can, just understand the knowledge at a little bit of a greater depth. Well, they're actually tethered to the wall of the apical surface of those columnar epithelial cells lining the alimentary canal, or in this case, lining specifically the small intestine. So they are what we refer to as brush border enzymes. So we have further brush border enzymes, which will then break down the maltose, finally cleave that final link between the two glucose molecules of the disaccharide maltose to give you glucose. Now let's go back and look at the disaccharides, lactose and sucrose. So lactose is milk sugar. It's just a combination of glucose and galactose. And both glucose and galactose are monosaccharides, right? I think you knew that glucose was a monosaccharide, but I just wanted you to remember that galactose is in fact also a monosaccharide. So what happens is with lactose is broken down by another set of, or I should say just not another set of, but another type of brush border enzyme called lactase. And it's going to break it down into glucose and galactose. So now we have separate glucose and galactose monosaccharides resulting from the breakdown of the lactose. Sucrose is a disaccharide that's a combination of glucose and fructose. Fructose is also a monosaccharide. So we also have a brush border enzyme called sucrase, which is going to specifically break down the sucrose into glucose, like we have here centrally as a product of the breakdown of maltose and lactose. And then we also have fructose resulting from the breakdown of sucrose. So finally, as a result of all of these different interrelated enzymes working together, we have the monosaccharides, galactose, glucose, and fructose, resulting from our breakdown of these major types of carbohydrates that we take in through our diet. All right. So again, here's just another summary of these individual enzymes, brush border enzymes, that are breaking down the linkages between the monosaccharide molecules in these disaccharides, maltose, sucrose, and lactose. All right, so now we're talking about the chemical digestion of proteins. If you guys remember, the subunit molecule of proteins is the amino acid. And we have 20 different types of amino acids in the body, right? So we're going to take in these very large proteins, and we're going to chop up all the bonds between the amino acids, which are called the peptide bonds, right? And then we're going to result ultimately in the individual amino acids. So the process works like this. We secrete an enzyme from our stomach called pepsinogen. We already gave reference to pepsinogen in the digestive system packet, the main packet that we went over. The hydrochloric acid that's also secreted in the stomach is going to activate the proenzyme pepsinogen to turn into the enzyme in its active form, which is called pepsin. And as the name suggests, pepsin breaks down peptide bonds. And as we break down the peptide bonds, we actually get just larger polypeptides resulting from the protein. So just as a reminder, a protein is when you have 50 or more amino acids linked together by peptide bonds. Now, a lot of proteins are much bigger than 50 amino acids, and this pepsin cannot break down every single amino acid, cannot break down every single peptide bond between all of the amino acids of these very large proteins all at once. So it just kind of randomly is going to break peptide bonds here and there, and so what you're going to initially get is just these larger polypeptides, which were once part of a larger sized protein. Does that make sense to everybody? So then we can further break down those larger polypeptides with other similar enzymes. So once we get into the stomach, we have other enzymes waiting for us. These are called the enteropeptidases. And these enteropeptidases, and these are just examples of them, trypsin, chymotrypsin, and carboxypeptidase, are all just going to do the same thing. They're just going to continue to work on these peptide bonds. Now, these enzymes, trypsin, chymotrypsin, and carboxypeptidase, actually are the product of proenzymes, or precursor enzymes, trypsinogen, chymociprinogen, and procarboxypeptidase. These enzymes are activated by another enzyme that's secreted in the small intestine, enteropeptidase, and then the enteropeptidase is going to activate these enzymes into their active forms, trypsin, chymotrypsin, and carboxypeptidase. Enteropeptidase has an interesting story, by the way, one of the first purified enzymes. So, chymotrypsin, trypsin, and carboxypeptidase are just going to do the same thing that the pepsin did, except that it's going on in the small intestine. We're going to take these larger polypeptides and we're going to break them down into smaller polypeptides. And then finally, We have brush border enzymes like aminopeptidase, dipeptidase, and carboxypeptidase that are going to further break down those small polypeptides into individual amino acids. And then finally, those individual amino acids will be absorbed by our columnar epithelium and eventually get into our blood. Digestion of lipids. Now we're talking about digestion of lipids, we're really talking about the glycerides. And you know the basic subunit molecule of the glycerides are glycerol and fatty acids. So for example, triglycerides, which are the most common type of glyceride, have 3 fatty acids linked to a central glycerol backbone, glycerol molecule. Okay, so we're going to talk about triglycerides here. So bile helps to break down the big droplets of triglycerides into small droplets of triglycerides, but that's just physical digestion. So after the bile does its work, you're still left with just triglycerides, but albeit in smaller fat globules. Pancreatic lipase, however, which is part of your pancreatic juices, is going to actually chemically break down those triglycerides, and it's going to turn them into fatty acids and glycerol. And then those fatty acids and the glycerol can be absorbed through the columnar epithelial cells lining the intestines. So now, digestion of nucleic acids, don't worry about digestion of nucleic acids. You guys have enough to worry about. I always run out of time anyways in lecture to talk about this, so don't worry about that. And I did indicate that to you in the GI physiology notes with answers that were posted on Blackboard. So just, that should be nothing new to you, that we don't want you to have to memorize all that. All right, so not such a big deal. Again, I don't want you to know all of the specific enzymes that we have listed here, but I do want you to understand the basic idea of what we're doing, in terms of breaking down a large molecule into its subunit molecules. You should be able to know that you break down the carbohydrates into monosaccharides ultimately, and that this occurs over multiple steps across the GI tract, finally ending in the ultimate breakdown via the brush border enzymes tethered to the small intestine. Same concept with the proteins is we systematically break down the proteins by cutting them into increasingly smaller polypeptides, and then finally the brush border enzymes cut up the smallest of those polypeptides into the individual amino acids, which are absorbed through the columnar epithelium. And then with the lipids, specifically the triglycerides, it's basically just the pancreatic lipase itself that just chops up all of those bonds between the fatty acids and the glycerol, and then we're able to just directly absorb the fatty acids and the glycerol. So digestion of carbohydrates and proteins is a rather long process that occurs over several organs, whereas the digestion of lipids is primarily just occurring in the small intestine. Now, you will learn in lab that we do have an enzyme called lingual lipase that's secreted as part of our saliva that also does the same thing as the pancreatic lipase, but it's secreted in such small amounts that it really does not have a physiologically significant effect. But technically, yes, the digestion of lipids does begin in the oral cavity as a result of lingual lipase. All right. And by the way, when I said the enzymes that I don't want you to worry about, I'm talking about all of these enzymes, like, for example, dextranase and glucoamylase, trypsin, chymotrypsin, carboxypeptidase, enzymes that I do, or aminopeptidase, dipeptidase, carboxypeptidase. I would like you to be aware of. Let's just go through and I'll have you circle the enzymes I want you to know. Of course, I want you to know about pepsin, and I want you to know that pepsin results from the activation of pepsinogen via hydrochloric acid. I'd like you to know, maltase, sucrase, and lactase, because their names suggest their action quite easily. I'd like you to know about salivary amylase and pancreatic amylase. for the digestion of carbohydrates. And I'd like you to know about pancreatic lipase for the digestion of triglycerides. All right, so again, let's just go over the enzymes I do want you to be aware of. Salivary amylase, pancreatic amylase, maltase, sucrase, and lactase, pepsinogen and pepsin, and then pancreatic lipase. You should be aware of all those enzymes and know with respect to the larger biomolecules that they play a role in breaking down into their respective subunits. All right, so the last thing I want to go over is absorption. So let's go to the OneDrive here and find our absorption answers notes. So this is pretty straightforward. We already gave reference to the absorption of these different subunit molecules. So as far as the absorption of the monosaccharides that we talked about, like for example, the absorption of glucose or galactose or fructose, that's just absorbed directly through these columnar epithelial cells at their apical surface. And those monosaccharides are absorbed via both active and passive processes. So same thing with amino acids. We just take those different types of amino acids in through the apical surface of the columnar epithelial cells. They are then transferred, whether we're talking about the amino acids or the monosaccharides, to the basolateral surface, and they eventually end up in the blood coursing through the capillaries. Right? And we're talking about the capillaries that are within the lamina propria and the submucosa. And eventually those capillary beds are drained by the veins, which eventually spill into your hepatic portal vein, and all of those nutrients are taken to the liver for detox and processing. Okay, so now let's talk about absorption of lipids. When we're talking about very small fatty acids and glycerol, we can take those substances directly in through the apical surface of the columnar epithelial cells. However, when we're talking about very large fatty acids, then we have a different system. So the very large fatty acids basically I misspoke when I said glycerol. Glycerol has to go in through the way that I'm just referring to here. It's the short fatty acids that can come directly in through the apical surface of the columnar epithelial cells. But when we're dealing with glycerol and very long fatty acids, or possibly even monoglycerides, which is a glycerol joined to a fatty acid, these molecules get bunched up into these little globs of lipid called micelles. And the micelles actually get absorbed through the apical surface of the columnar epithelial cells as a whole, like a big glob. Then what happens is you have to have reprocessing of these large fatty acids and monoglycerides and glycerol. So we take those molecules, we break them down as much as we possibly can, and then we rebuild the small triglycerides that our body can handle better. And those triglycerides then are going to leave these cells at their basolateral surface, these columnar epithelial cells, in the form of these protein-coated structures called chylomicrons. And chylomicrons, because they're coated with proteins, are more soluble in our bodily fluids. And they're not uploaded onto the blood. Believe it or not, they're uploaded into the lymphatic vessels that you find within your mucosa called lacteals. And so those lacteals then end up spilling into our greater lymphatic system. So you have all of these kind of globules of fat called chylomicrons floating through your lymphatic system, and they eventually flow back to the venous side of your systemic circulation. And that's how they ultimately get into your blood. All right, so that's all we want you to know as far as absorption goes. Nothing more than what's written here on this handout. All right, so that is the digestive system. Again, I want you to just pay close attention to those enzymes that I emphasized previously when we talked about the digestion of carbohydrates, proteins, and triglycerides, and I think you'll be okay. All right. I can't think of anything more that I want to add right now. Oh, and as far as the overall proportion of the physiology questions to everything else, the vast majority of the questions are going to be on the material that was in our main digestive system packet, which mainly covered material relating to anatomy. So the physiology material is something that you're going to get more of in an application-based delivery. And so most of your assessment for this knowledge is really going to come from lab. All right, so that's it then.